Okay, so I've now got a better document camera, so hopefully this is looking a lot better for you, and I'll get feedback from whether or not it is. To keep the videos a little shorter, I've broken it up into two parts. So this is 9.A, the first sections of the content, and you should have a printout or are able to follow along with the Word document that I posted. So a hypothesis test is a statistical statement about one or more parameters. And that statement can be about a parameter that is the mean, the variance, you can do it on the median, on the mode. So statistical statement about a parameter. And it's for a parameter of a given population. And that's important that our statistical testing is always being done about a population, and we're comparing a sample to that given population. And so when we are doing a hypothesis, we can do it in two ways. We can write a two-sided hypothesis, which would say that our null hypothesis, and that's our correct verbiage here, is a null hypothesis. And we give that in the form of H naught or H0. And we're going to say that there's a mu, a mean, set equal to a certain number. Our alternative hypothesis is actually that just that the mu is not equal to 50. And so we give that the designation H1, and it's not equal to 50. So a two-sided hypothesis is either equal or not equal. For a one-sided hypothesis, you can do, again, the null hypothesis would be an HO is mu is equal to 50, and the alternative H1 is that mu is less than 50. And so that would be looking at the lower half, one-sided, or you could do that the null hypothesis is mu is equal to 50, and the alternative hypothesis is mu is greater than 50. So with our one-sided hypothesis, we're either going to be looking above or below the mean. Our two-sided hypothesis, we look at equal or not equal. And so we're going to collect information from a random sample of the population. And we're going to talk about this because hypothesis sampling, hypothesis testing is looking at a particular random sample, but then we're also going to have levels of confidence on what other samples might be found to be true or false using this hypothesis. And so if the information that we gather in our testing is consistent, then we say that we know that the hypothesis, and I'm just going to abbreviate that, HYPO, hypothesis is true. Another way to say that is to fail to reject. And another way to say that is to accept. So when we're looking at the hypothesis, if the information is consistent, either we say it's true, we fail to reject it, or we accept it. The other way to say it is if the statistical analysis shows that it's inconsistent, then we would say that the hypothesis is false, and we reject it. So if it's true, we have failed to reject it, the null hypothesis, and if it is false, then we do reject null hypothesis. So this is all in response to the null hypothesis. So your HO. And again, this is also the null hypothesis, HO. So all of our statistical testing is done with respect to that. So if we're going to look at a region, we could draw this out and we could say that there's a critical region between 58.5, and this is a typo on my handout. I think I fixed it on yours. So 58.5 and 51.5. And so we're going to say that there's this region. And so we have 48.5 as our lower bound. We have 51.5 as our upper bound. And we've got a population mean of 50, so right in the center of that. And so then we're going to say that below 48.5, we would reject the null hypothesis. And above 51.5, we would reject the hypothesis. But the critical region, anywhere between those two criteria, we would accept the null hypothesis. So this means if our sample mean X bar is between 48.5 is less than or equal to X bar, which is less than or equal to 51.5, we're going to accept HO. But if our X bar is less than 48.5 or our X bar is greater than 51.5, we are going to reject HO. And that is the basic premise of hypothesis testing. And so we have probabilities associated with this. And so the likelihood of rejecting a null hypothesis, even when it is true, is signified as alpha. And so we call this type 1 error. And we note that by the letter alpha. And it means the probability to reject the null hypothesis, even though HO is true. Now, the other issue you could have is a type 2 error, and that means we accept the null hypothesis when it's false. And so type 2 error is equal to beta, and that means the probability we accept HO even though HO is false. And so we can calculate what those probabilities are using our old Z statistic. And so we remember that our Z statistic is equal to X bar minus mu over sigma divided by the square root of n. And so we can calculate type 1 and type 2 error. And so the first one is calculate type 1 error. And so our type 1 error means that we're calculating alpha, and that is the probability that X bar is less than 48.5 when mu is equal to 50, and the probability that X bar is greater than 51.5 when mu is equal to 50. So this is the same thing that we were looking at before. We were saying that we had this region that is between 48.5 and 51.5, where we expect our sample means to fall if we know that the population sample is 50. And so we are given an n of 10 and a sigma of 2.5. And so first, the probability that X bar is less than 48.5 is equal to 48.5 minus 50 divided by 2.5 over the square root of 10. And so that is equal to negative 1.5 divided by 0.79. And that gives us a z-statistic of negative 1.9. And so I looked that up on the table, and I find that that z-statistic of negative 1.9 is equal to 0.0287. Now the probability that x bar is greater than 51.5 is equal to 1 minus the probability that x bar is less than 51.5, because remember, our z-table is always going to the left. So I need to do 1 minus. And so I'm doing 1 minus the probability that 51.5 minus 50 over 2.5 divided by the square root of 10. And so that equals 1 minus my z-statistic of positive 1.9. You can't see the decimal there, 1.9. And that is equal to 1 minus 0.971283 from the back of your textbook, which is equal to 0.0287. And so our alpha is equal to 0.0287 plus 0.0287, and that is equal to 0.0574. And what that means is that there's a 5.7% chance that we are going to reject an H bar, an X bar, reject X bar when mu is equal to 50. So 5.7% of the time, there'll be a sample that actually is from a population that has a mean of 50, but because that X bar is too far away from the sample mean, we're going to reject it, even though it is a sample from that given population. And so 94.3% of the time, we're actually going to have an X bar that's within the critical region. So 94.3% of the percent of the time, we're going to have an X bar that is within that critical region between 48.5 and 51.5. So that's what we're looking at for there. Now, we can increase our alpha level in two ways. Either increase the critical values, and those critical values are the actual changes, right? Like the actual 48.5 and 51.5. So if I spread that number line and I move that 48.5 down to maybe 47.5, and I move that 51.5 maybe up to 52.5, I could extend that alpha. The other way is to increase the sample size. And this is one of the things that we continue to talk about, that as we increase the sample size, our values become more in line with what we're actually hoping to achieve, because our X bar is getting closer to our actual population. So as N increases, our alpha would also increase. So what about type 2 error? Well, type 2 error can be written as beta, which is the probability, and it's 51.5, still the same critical region. 48.5 is less than or equal to X bar, which is less than or equal to 51.5, and I think yours has it correctly, but mine keeps having it wrong. So beta is equal to the probability that we're within that critical region but the mu is different than we thought it was. That instead of the mu being 50, the true population is actually 52. And so we're within this region, and we're afraid that we're going to fail to reject the null hypothesis. So we're going to accept the null hypothesis for a given critical region, but we had our mu wrong. We had done this based on a mu of equal to 50, but the true mu is 52. So if you think about it, if you have this data and you think that the mean of a process is equal to one number, but it's actually equal to something else, then your critical region is off, right? So we're going to calculate this type 2 error, the likelihood that we were using the wrong critical region. And so we accept a sample, but we're accepting the sample under a false pretense. So beta is equal to then the probability that 48.5 minus 52 divided by 2.5 over the square root of 10 is less than or equal to z is less than or equal to 51.5 minus 52 over 2.5 over the square root of 10. And so we're looking at the probability of the z value between those two bounds. And so that's looking at the probability that we're between negative 4.43 and negative 0.63. Those are our z values when we do the math for this expression here. And so to do that, we're looking at the area of the area under the curve of those two locations. And so we're actually looking at the probability that z is less than or equal to negative 0.63 minus the probability that z is less than or equal to negative 4.43. And so these we just look up on the table as they are. And so that negative 0.63 is 264,347. And then negative 4.43 is all the way off the table at 0. So we know that the probability that we would accept a mean in the critical region under false pretenses is 26%. The final thing that we can look at in this section, looking at the power of a statistical test, the power is equal to 1 minus beta. And so like in this case, we would say that 1 minus beta is equal to 1 minus 0.264347. And this is looking at the likelihood that we would actually have the correct sample, and that's equal to 0.7357. And so we'll talk more about power later when we do more in the hypothesis testing, but it's equal to 1 minus beta, so I figure we'll throw that in now. So we have a problem given to us here. So there's a cement mixture normally distributed. The mean is thought to be 70. The standard deviation is 2. We're testing a null and alternative hypothesis with a sample of 5 specimens, and we're given an acceptance region, and so we're trying to find the type 1 error or alpha. And so the type 1 error is, again, as we said before, when we're looking at type 1 error, we're rejecting the null hypothesis even though the null hypothesis was true. So we're looking at the idea that we have an X bar that is lower than that 68.5 or an X bar that is higher than that 71.5 with a true mean of 70. And so our alpha is going to be equal to the probability that there's an X bar lower than 68.5 plus the probability that there's an X bar greater than 71.5. And so we calculate those again using the Z statistics. And so we're looking at an X bar minus mu over sigma divided by the square root of n as our Z statistic. And so we have that alpha is equal to the probability of 68.5 minus 70 over our standard deviation of 2 divided by the square root of 5 plus the probability, again, we're doing 1 minus the probability of Z being less than 71.5 minus 70 over 2 over the square root of 5. And so we have values of the probability of z is less than or equal to negative 1.68 plus 1 minus the probability that z is less than or equal to 1.68. All of these equations have been symmetrical so far. They don't have to be. You don't have to have a symmetrical region, but you often do. And so that is equal to 0.046 plus 1 minus 0.954, which is equal to 0.092. And so our alpha is 9.2%. Now we're looking at beta and we're saying, well, what if the actual true mean was 73? We thought it was 70, but it's actually 73. If you use that same acceptance criteria, how often are we going to fail to reject or accept a null hypothesis even though it's false? And so our beta is equal to the probability that there's an X bar in between these two regions when mu is actually equal to 73. And so that is equal to the probability of 68.5 minus 73 divided by 2 over the square root of 5 plus the probability of 71.5 minus 73 over 2 divided by the square root of 5. And so that is equal to the probability that z is between negative 5.03 and negative 1.68. And so again, you look up those z values on the table, you have 0.046 minus 0, or 0.046 as beta. And so if you look at a p-value, the final thing we'll work on calculating today is the p-value. And the p-value is looking at the smallest level of significance that would lead to a rejection of HO. So how tight can your data be? So if we look at a normal curve and we have a given mean mu, and then we have these tails where we're rejecting a sample mean, even though they are within the distribution, we're looking at the p-value being the smallest level that would lead to a rejection of that hypothesis. And so we calculate the p-value as being 2 times 1 minus the z statistic for that z value for that given x bar. And so in this case, we're looking at 2 times 1 minus 51.3 minus 50 over 2.5 divided by the square root of 16, because we're still using our z statistic as z is equal to x bar minus mu over sigma divided by the square root of n. And so 2 times that z statistic is equal to 2 times 1 minus the z statistic of 1.3 over 0.625. And so that's equal to 2.08. And if you look 2.08 up on the table, sorry, kind of lost me there for a second. 2.08 on the z table is equal to 0.981237. And so we're looking at 2 times 1 minus 0.981237. And so that is equal to 2 times 0.01876, which is equal to 0.0375. And so you're looking at a p-value. P is equal to 3.75%. So based on the given true mean of 50 and a sample size of 16 and a standard deviation of 2.5, if your observed sample was 51.3, we're looking at only 3% of your, we're looking at only 3.75% of your data points are going to give you an X bar of 51.3 and accurately represent that 50 mu. So only 3% of the time is that 51.3 actually going to adequately represent the population. Again, increasing the sample size would be a way to increase the power of that and increase your p-value. So we're going to calculate a couple p-values. I'm going to try to zoom back in. So just practicing calculating a couple of p-values. They're saying calculate the p-value based on the given mean. So our hypothesized mean, our null hypothesis is that the mean is equal to 4, and our standard deviation is 0.25 for all of these. Our n is 0.8 for all of these. So we're going to calculate the z-statistics for all of these cases, and this is just giving us a chance to practice. And so our z-value for the first one, 4.1, is 2 times 1 minus the z-statistic for 4.1 minus 4 divided by 0.25 over the square root of 8. And so that's 2 times 1 minus the z-statistic for the value of 1.13. And that means you have 2 times 1 minus 0.8711 based on the table. And that is actually equal to 0.258. So what about if your sample mean is 4.2? Well, here you have 2 times 1 minus the z-statistic, 4.2 minus 4 divided by 2.5 divided by the square root of 8. And that's equal to 2 times 1 minus the z-statistic value for 2.26. So we look up 2.26 on the table and we get 2 times 1 minus 0.9881. That is equal to 0.024. And then going the other way, 3.8. Here we're actually going to look symmetrically, which means we're going to get the same answer because we have 2 times 1 minus the z-statistic for 3.8 minus 4 over 0.25 over the square root of 8. So our z-statistic is just looking at the other side of the curve. So 2 times 1 minus the z-statistic for negative 2.26. And so we're actually looking at 2 times 0.0118. And that is equal also to 0.024. And so these are the same because we're symmetrical distance away from the mean. We're 0.2 away from the mean. So if you were looking at 4, 3.8 is 2 below it, and 4.2 is 0.2 above it. So those answers are always going to be the same. So this is just giving you some practice with the z-statistic, and the next video will do the remainder of the chapter. As always, if you have any questions, let me know, and on Thursday we'll do a simultaneous activity so that you are able to ask me questions if you have any. Have a good day.